Hey there, chemists. In this lesson, we're going to look at what are called enolates, how we make them, and how we use them. Enolates are essentially an anion on what I'm going to call an alpha carbon. Alpha meaning right next to a carbonyl. And in this general box here, I intentionally put just the variable x, meaning we'll see that you could make an enolate from a variety of things, having a negative charge there. This could have been a ketone, this could have been an ester. We can make enolates out of amides and all kinds of other carbonyl containing compounds. So let's take a look at what we do with them. Here in the beginning in the upper left is an example of just a ketone. We have acetone, and it forms the enolate upon treatment with LDA. LDA is an acronym of a very big base we learned about last semester. I'll show it down below. Stands for lithium diisopropyl amine. Actually, amide. And I almost said amine because it comes from diisopropyl amine. So let's draw diisopropyl amine. That's two isopropyl groups attached to a nitrogen. That's diisopropyl amine. If you treat this with a very strong base, you can get rid of that H and get the conjugate base of a base. In other words, the nitrogen anion. And then there's just a lithium counterion, usually made from something like N-butyl lithium. That's what the molecule looks like. It is a non-nucleophilic base, and that just means it's very bulky, so it's never going to accidentally do an SN2. It's not going to happen. It will act as a base and take away an H from something, and then make the conjugate base of that thing. So we're never going to have LDA attacking the carbonyl. Instead, it will deprotonate one of the alpha hydrogens that we have here. In fact, let's show that. Let's see the mechanism of this. Everyone make some space and redraw acetone. And I want you to actually draw out the 3 alpha hydrogens that are on the adjacent carbon right there. And then I'm going to abbreviate LDA with just the acronym. And let's see the arrow pushing for this. LDA is a base. It takes away the H. And you break that CH bond, and that CH bond sends a pair of electrons right on the alpha carbon. So you get a lone pair and thus a negative charge on that carbon. This should look very strange because we never deprotonate hydrocarbons, but we can do it here because this is a resonance-stabilized anion. That negative charge can delocalize to become a carbon-carbon pi bond and make its way up to the oxygen. So you can actually get an oxygen anion. And that's the enolate. One could argue the one on the right is actually the more significant contributor because the negative charge is on the more electronegative oxygen atom. However, most of the time when we look at the reactions we'll see in this class, we use this version, meaning something happens attaching to that alpha carbon, and this is what acts as the nucleophile. In fact, that's indeed the case. When we look at this generic example, this is the resonance-stabilized anion, but let's see what it does when it looks at an SN2 acceptor. For example, bromoethane. Well, we form a bond, if you look at the product that's up above, between the alpha carbon and that carbon attached to the leaving group. There's your new bond right there. So how this must have happened is that oxygen anion comes back down to reform the carbonyl carbon, and the pi bond attacks the carbon attached to the leaving group. This is just an SN2. And you might say, why doesn't it attack from the oxygen? Doesn't that make just as much sense? There's a couple of reasons we can use to explain that. I'll tell you one. In this case, it's more thermodynamically favored to get the more stable carbon-oxygen double bond out of it. That's just a more stable molecule. And there's actually cases where you do get attack from the oxygen. It largely depends on what the acceptor is and what else is true about the conditions of the reaction. But for most of the time, we're going to see things getting attacked from the alpha carbon. Now, this is a pretty good enolate. This is pretty good in terms of its resonance stabilization, but we're going to work with enolates that are even better. And here's one that comes from what's called a beta keto ester. This is a beta keto ester, and the name simply comes from the fact that it has an ester. There's the ester, and the alpha carbon is right in the middle. One more away is the beta. This happens to be a ketone, so beta keto ester, and there's where the name comes from. Go ahead and draw in the alpha hydrogens that are on this particular beta keto ester. There's 2 of them, and this time they're flanked by 2 carbonyls. So what happens is what we have here is a base. In this case, you don't need as strong of a base as LDA. You can actually deprotonate this with a regular old strong base like ethoxide. Draw an arrow from the ethoxide to one of those CH bonds, and that will put a negative charge right in the middle of this molecule. You'll get an anion sitting right on the alpha carbon that's flanked by 2 carbonyls. One happens to be an ester, and one happens to be a ketone, but that's a really good resonance stabilized anion. Not only do I have delocalization up into the ketone, you could also imagine delocalization up into the ester. So this is a much more stable anion, more stable enolate. I'm not going to draw those resonance contributors, just wanted to highlight them like that so that you can see them, and hopefully you can realize if you had to draw them, you certainly could. Now let's use this and do an SN2 with part 2, the SN2 acceptor. So if I treat this with bromoethane, draw an arrow from that negative charge to the carbon attached to the leaving group. The leaving group leaves. You get a new bond between the center carbon and the carbon that used to be part of the bromoethane. And there's your product. And you could imagine doing other things to this if we wanted to. Why is this relevant to what's right up above? Well, I said this is a much more stable anion that you can form in the beginning. And think about our most recent unit related to carboxylic acid derivatives. You could certainly treat this with saponification conditions and saponify it so that that ester becomes a carboxylic acid. Or any number of other things, frankly. So the OET simply becomes an OH. That's just the keto acid instead of a keto ester. And there's actually a way to get rid of a carboxylic acid as long as it's right next to another carbonyl, which means once I have this, you can turn it into a regular old substituted ketone, which is buried right there. And that's what this next part is all about. It's called decarboxylation. So let's read. Beta keto acids, aka the thing we just made, and esters, beta keto acids or esters, can undergo a thermal decarboxylation as shown below. The product is an enol, which undergoes tautomerization. That's a good old word from first semester. In order for this to occur, there must be a carbonyl group, beta 2, an acid. For example, here is a carboxylic acid. There's the alpha carbon, meaning alpha relative to the carboxylic acid. And then one away from that is a beta position. So I have a beta carbonyl. Happens to be a ketone, but it could certainly be an ester attached to the carboxylic acid. It could be just about anything. It could be an amide if you wanted to have one of those other carboxylic acid derivatives. As long as the acid is that many carbons away, it could be an aldehyde, as long as it's on the beta carbon relative to the carboxylic acid. If you have that arrangement, you actually get to lose the entire carboxylic acid that's attached. In fact, this even works if you have a carboxylic acid. I could have 2 carboxylic acids and then we can lose one of them in a decarboxylation. We're left with the other. It has to stay put because once you lose one, it no longer has a beta acid. You'll see what I mean when we do some examples. Anyway, let's add curved arrows to this and you'll see how it works. So the beta keto acid, they just redrew. So we rotated around this carbon-carbon bond, and that gives us just a different representation of the molecule right here. It's the same thing. All you have to do is heat this up. Remember, the triangle means heat. That will lose a carbon dioxide. And I want you to see if you can figure out how that happens. Here is a carbon dioxide molecule. See if you can hit pause and draw curved arrows on top of this structure to show how it turns into the enol and a CO2 molecule. Try that now. Okay, so welcome back. Let's see what we did. Notice the bonds that break and the bonds that formed. We formed a new OH bond. There it is. So I'm going to draw an arrow from this oxygen to that H. We also broke the pi bond right here. So I'm going to draw another arrow that shows that pi bond going up to the oxygen. You actually can combine those arrows if you want to. You could just have one curved arrow that looks like the pi bond to the H. That is also okay. The rest of these, though, you'll see have to follow suit with what we're about to show. We break a carbon-carbon bond right there, and we form a carbon-carbon pi bond right there. So I could do that with one arrow from that bond to that bond, right to left. There's only one more. We have to show the breaking of the OH bond up here, and then there's a forming of a CO bond. It's in the carbon dioxide. So that OH bond is going to become a CO double bond. And what you get is the enol and then a carbon dioxide. Hopefully you can see where this actually is this pair of molecules. So we lose that whole CO2 group because of this arrangement. Then it undergoes a tautomerization. That's essentially the pi bond picking up that extra H. The OH breaks and you form your carbonyl. So as long as you have a carboxylic acid beta to anything else, you can lose it and become a substituted ketone or substituted whatever that other carbonyl is. But they have to be in this relative arrangement to each other. So as an example, off to the side, I'll just show another example. If you had a beta diacid, you could heat it up. You would lose the carboxylic acid, one of them, but you would keep the other one. So if I had something like this, I would lose one of them as a CO2 molecule. And if it's substituted with, let's say, an R group, you get to keep that substitution. Hence, the example right up above it, I could turn this into a substituted ketone. Why is this meaningful? It just means we get to start with a much more useful molecule that turns into an easy enolate. And these are often commercially available. You can buy a number of different types of simple beta keto esters and similar types of molecules. And what's more is we're going to learn how to make them in just a few lessons, so they're coming. They can be made from simple building blocks as well. Okay, let's learn one more thing about enolates, which is that they can undergo conjugate additions. Remember, a conjugate addition is what happens when you have, let's say, an unsaturated ketone and a cuprate. A cuprate is an organometallic, and it would attack in a conjugate sense. It wouldn't hit the carbonyl carbon, it hits the beta carbon, and you get substituted ketones. Well, enolates will do the same thing that cuprates do. They'll attack unsaturated carbons, but in a conjugate addition. So in the presence of base, let's draw in our alpha hydrogens and form the enolate. That's always going to be your first step. So the base takes one of those H's away, the CH bond breaks, you get an enolate. That is going to be the first step in every single one of our mechanisms in this unit. Form the enolate. Which just means you put a negative charge right on that carbon. Then this will react with the enone. You'll do a conjugate addition. So I'm going to redraw the enone. How do you do a conjugate addition? You have a nucleophile. In the past, we've seen cuprates, but now we just have a negatively charged carbon that's part of this enolate, and it will attack the beta carbon. So draw an arrow from that enolate to the beta carbon. That sends the pi bond right to that alpha carbon. It's going to give a big molecule. It's going to combine these two things into one thing. Let's see what we get. I'll redraw those two esters that were part of the original enolate. And now we have a new bond between this carbon and this carbon. So I have a new carbon-carbon bond, and now I have 1, 2, 3, 4 extra carbons, including the one that I just drew. So 1, 2, 3, 4. What else do I have? I still have this ketone, one away from the end. And I still have, I now have a new negative charge on that carbon right next to it. So I have a negative charge right there. In fact, heads up, that's an enolate. That's a negative charge right next to a ketone. So we just made a new enolate. Now, conjugate additions, if you forget how they work, the next step is just filling up that negative charge with a proton source. And we're in ethanol, if I look back at the original part, so that anion can simply take an H from ethanol, which means you regenerate ethoxide. Notice in these mechanisms so far, we're in base, so I'm seeing a lot of negative charges. Remember, a lot of the mechanisms we've done this year are in acid, and that's when you see positive charges. But now we're finally in basic conditions, so we're in negative charges. That might look nothing like the product, but it actually is the same molecule that we have over here. What do I have? I have a 4-carbon chain with a ketone tethered to it. Yep, there it is. And then off of this mostly substituted carbon, I have an ethyl ester and a second ethyl ester. There they are. I just drew one of them out and abbreviated the other one. And if I wanted to, I could certainly saponify these to make them OHs, and then decarboxylate 1 to give me a substituted keto acid. Okay, let's wrap up with one more thing. There's another type of conjugate addition that we can use. It's a conjugate addition that's an SN2 conjugate addition. We haven't seen this since last semester. This is via the formation of what's called an enamine. This is called an enamine. And an enamine is what you get when you react a secondary amine with a ketone. This is under acidic conditions, and then it will do a special type of substitution with this alkyl halide. Let's redraw that ketone, and we'll walk through what happens with this mechanism. The first step is obviously protonation of the ketone. So I'm just going to draw it as the oxonium ion, because that's your first thing. Then, our secondary amine will attack the oxonium carbon, send those electrons up. Now you have an OH and a new carbon-nitrogen bond. This is going back a couple units to amine chemistry. That's what all this is going to look like. Looks like if I look at the enamine product, I need to get rid of this OH. We are in acid, so I need to make a water molecule. So let's do a proton transfer from the from the N, where there's a lot of them, to the oxygen, where there aren't that many of them. That turns the OH into an OH2 with a plus. And now I have a nitrogen with a 5-membered ring. And then to get to the enamine, that water molecule is going to leave. And at the same time as it leaves, the nitrogen can donate a pair of electrons, and you'll temporarily get an iminium ion. That's an iminium from a couple of units ago. How do you get from the iminium to the enamine? Well, look at what we've lost. We've lost one of the H's on that alpha carbon. So that water molecule that just left is actually going to act as a weak base and take away one of those H's. So draw an arrow from the water to the H. The CH bond breaks to give you a CC double bond, and that pi bond goes up to the nitrogen. And there's your enamine. That's only the first part of this. What's the point of this? Enamines are kind of like enolates. They actually behave very similarly to enolates. They have this nucleophilic pi bond, and they have an atom with lone pairs of electrons on the adjacent atom. So just like enolates can react where you reform the carbonyl and the pi bond attacks, we can have the same type of arrow pushing with enamines, but they're neutral. They're actually more stable than enolates, so you can make them and store them. In fact, this one is very famous. This is called the Stork enamine, named after a Columbia professor named Gilbert Stork, and he's quite well known. We're almost done here. What can we do with an enamine? We can do the same type of chemistry that we saw up above. I'll just show you an SN2. This is actually an SN2 prime. You might think, oh, this just attacks the carbon attached to the leaving group, and that gets me my new carbon-carbon bond. And the answer is almost. What happens instead is the pi bond actually hits the roomier pi bond here. That migrates via resonance and sends the bromide out at the same time the nitrogen donates, and you get a substituted iminium ion. 1, 2, 3 new carbons, and then I get an intermediate iminium. And I'm not going to go through the rest. I will let you look at what this does in the presence of water. You hydrolyze the iminium back to a ketone. That's actually a reaction we did a couple of units ago. But the point of that is that enamines are more stable than enolates, and they otherwise do the same kind of chemistry so far. There's a couple of things that make them different, and we'll see that going forward. Okay, so that's an introduction to enolates and also enamines and how we can use them with a focus on decarboxylation when there's a beta acid. And moving forward, we'll see how enolates can actually react with carbonyls.